All right, continuing on with nucleophilicity parallels basicity, we need to look at some general rules. Recall that usually a strong base means it's a strong nucleophile, so how strongly a nucleophile will attack a carbon parallels or is very similar to how strongly that same beast would attack a proton. OH minus hydroxide is a strong base. We know hydroxide is a strong Bronsted base. Therefore, we can predict it'll be a strong nucleophile. Not only does it like to attack protons, it likes to attack carbons, partial positively charged carbons also. All right. Some things to note. If you have the same nucleophilic atom, the stronger the base means the stronger it is as a nucleophile. For example, here, if we have hydroxide, the atom with the lone pair on it is oxygen here, versus acetate, the atom with the lone pair is the oxygen also, but we know hydroxide is a much stronger base than acetate ion because water is a much weaker base than acetic acid. Therefore, since hydroxide is a stronger base, it is the stronger nucleophile also. Note, if your nucleophile has a negative charge, then it is a stronger nucleophile than the conjugate acid. Note, hydroxide has negative charge. The conjugate acid of hydroxide is H2O. H2O is neutral, which means hydroxide is the stronger nucleophile. We'll also see this quite a bit if I had CH3OH versus CH3O minus, put in my lone pairs, which of these two is the stronger nucleophile? They both have oxygens with lone pairs, but which is the stronger nucleophile? That's right. CH3O minus methoxide is the stronger nucleophile because it is the conjugate base form of these two. This is the acid form, this is the base form. The base form has a negative charge. It is the stronger nucleophile than this. This is a strong nucleophile. We would classify this as a weak nucleophile. All right. And note, if we're going across a periodic table, F minus is not that basic. It's a little basic. It's a weak base. Hydroxide is a strong base. Amide ion, NH2 minus, a very strong base. CH3 minus, methide ion is an extremely strong base, which makes it an extremely strong nucleophile. All right, so good deal. Nucleophilicity, parallels basicity, we got that down, but you know, the world sometimes runs on exceptions. And we have exceptions to these rules. Sometimes steric effects will come into play and cause nucleophilicity to not parallel basicity. And we'll look at some other exceptions also. The prime example is tert butoxide. This is a carbon with 3 methyl groups on it and an O minus. This is the conjugate base of tert butanol. Just put a hydrogen on here, and this would be tertiary butanol, tert butanol. So we get rid of that hydrogen. It's the conjugate base of tert butanol. We would expect this to be a strong base, just as CH3O minus is a strong base. And it is. This is a nice, strong base. It's a good, strong base. It loves to take protons. It's even stronger base than ethoxide, CH3CH2O minus. However, ethoxide is a much stronger nucleophile. The deal is, when you look at molecules, and here I've got my good old cyclohexane ring here, note, the carbons are all on the inside. The hydrogens tend to be on the outside of the molecule. The hydrogens are always facing out. It's the carbons that are on the inside. If something's going to act as a Bronsted base, it just has to snag one of these hydrogens. Well, the hydrogens are on the outside. That's pretty easy to do. If it's going to act as a nucleophile, it's got to attack one of these carbons down in here. It's got to get past all of these hydrogens that are causing a bit of steric hindrance. The more steric hindrance you have, the harder it is to attack that carbon. If you have a tert-butyl group here, and you had an oxygen attached right here to this inner carbon right here, and you wanted that oxygen to attack a carbon in this molecule, these methyl, look at that fight, yeah, these methyl groups are going to block this oxygen from getting close to this carbon. There's just too much steric hindrance. The more bulky the group is, meaning the more shrubbery, as one might say, the more substituents on the carbon that contains this oxygen here, the tougher it is for this oxygen to get into a positive carbon. Now, it's easy to snag a proton. Protons are on the outside, but it's very difficult for this guy to attack a carbon. So tert butoxide actually cannot act as a nucleophile. It will not attack carbons. It can only function as a strong base. So here we have something that's a strong base. A strong Bronsted base will snag hydrogens like nobody's business, but will not attack carbons. Just it's too sterically hindered to attack carbons. All right. Just because we're talking about exceptions to the rules, here's something nice to just get into your head about other exceptions. Cyanide is a very skinny molecule. It's very thin. And the negative charge, if we look at cyanide, the Lewis structure for cyanide, we will see that it looks like this, where you have a lone pair on carbon. Well, we know lone pairs on carbon tend to be pretty strong nucleophiles, and that is what we find. Cyanide is a very, very strong, very, very good nucleophile. But realize cyanide ion is the conjugate base of HCN. HCN is a weak acid. Therefore, cyanide ion is itself a weak base. Being just kind of a weaker base, one would not expect it to be a good nucleophile. But it turns out it's a very good nucleophile. So cyanide is also an exception. Here we have a weak base that should be a weak nucleophile, but no, this is a weak base that is a strong nucleophile. SH minus, SCH3 minus are the same. They are weak bases, but they act as nice, strong nucleophiles. So that goes against our nucleophilicity parallels basicity. Nucleophilicity parallels basicity says weak bases should be weak nucleophiles. Nope, these are weak bases, but they're strong nucleophiles. This is a strong base that should be a strong nucleophile. Nope, this is a strong base that is an extremely weak nucleophile. So get to know the exceptions, because their exceptions are kind of what make things fun. Because if you have them memorized, oh, well, now we don't have to figure out anything. We know exactly what is going to happen. All right, so we've looked at the nucleophile. We've kind of looked at the leaving group. Let's now look at solvents. Now, the solvent effects that we're going to talk about here, we don't have to worry about them too much. We're going to find later in this chapter that that's one of our least bits of worries, except in one very important case that we must talk about. All right, so polar protic solvents, meaning solvents that have a nitrogen or especially an oxygen with a hydrogen on it, such as water, alcohols, acetic acid here. These are capable of hydrogen bonding, and so they really like anions. These protons have a very nice partial positive charge, because remember, OH is fairly darn polar. These hydrogens have a fairly good positive charge on them, and that's going to be very, very attracted to anions. Negative anions are attracted to the large hydrogen partial positive charge, which means water and alcohols really love cations, really love to solvate the cations really nicely. And it turns out they really like to solvate anions nicely too. Anions because the hydrogens have the positive charge. Cations get solvated because this oxygen's a fairly decent negative thing. All right. So in polar protic solvents, the nucleophilicity increases down a column. So this is actually different than what we expect from pKa's. We expect iodide to be a very, very good leaving group. and a poor nucleophile, because HI is a stronger acid than any of these guys. We expect F minus to be a fairly okay nucleophile, but a poor leaving group. And that is normally what we find in normal organic solvents, which are not polar protic. But if you run an organic reaction in a polar protic solvent, water or alcohols, we find out this reverses. We find out fluoride turns out to be a better leaving group. It's a weaker nucleophile because water likes fluoride better than it likes iodide. F minus, stronger, is a more compact, a smaller ion. Water really likes F minus. And so if you're running a substitution reaction in water, water is going to kind of prevent fluoride ion from becoming involved. Water doesn't want fluoride to be a nucleophile because then it has to give up the fluoride to the organic molecule. Water likes to pull fluoride off of organic molecules because it loves that tiny little F minus so much. So in polar protic solvents, our leaving group table gets reversed. Fluoride is a better leaving group. Chloride is not as good. Bromide's not a good. Iodide's not a good leaving group in polar protic solvents. If it's not a good leaving group, it means it's a stronger nucleophile. Iodide is a stronger nucleophile in polar protic solvents. Bromide is weaker. Chloride's weaker. Fluoride is a weak nucleophile in polar protic solvents. Note, if we go back to this table, that's the opposite of what we normally see. Looking at pKa's, fluoride should be a poor leaving group and a good nucleophile. And that is normally the case. Unless we're in a polar protic solvent, then fluoride is a good leaving group and a weak nucleophile. So note that distinction there. Most of the time, we're running our organic reactions not in polar protic solvents, but in polar aprotic solvents. If you've got a polar solvent that is aprotic, means does not have an OH or an NH on there, but especially OH, then our normal rules apply. And so here are our normal solvents that we use when doing substitution reactions. Acetone, great solvent. Acetonitrile, CH3, C triple bond M. THF, tetrahydrofuran, is an ether. DMSO, crazy good solvent, DMSO. DMF, dimethylformamide. Hexamethyl phosphoramide, HMPA. That's used a bit in biological chemistry. We don't do it too much in the organic land, but you do see it sometimes. So a lot of organic reactions run in acetonitrile, THF, DMF, very common organic solvents, even acetone. They are polar aprotic solvents. So note, since these are polar aprotic solvents, iodide is a good leaving group and a weak nucleophile. Fluoride is a weak leaving group, a poor leaving group, and a strong nucleophile in our normal polar aprotic solvents. But you need to have it memorized. You need to get in your head. If our solvent is polar protic, our nucleophilicity versus basicity gets shoved on its head here. Okay. So to summarize, to end this video about what we're seeing, we just summarized what I said here, but just what we're normally seeing in general. Increasing basicity means increasing nucleophilicity. The stronger something is as a Bronsted base, wanting to grab protons, the stronger it is as a nucleophile, wanting to attack carbons. Except with polar protic solvents, where that flips a little bit. Also, steric hindrance decreases nucleophilicity without decreasing basicity. All right. So, in our next video, we will start looking at the mechanisms of these reactions. Recall from Chapter 6 and from Gen Chem 2 mechanisms. What hits what when? What is the series of elementary steps that cause these reactions to occur? We will start looking at these mechanisms. There are two of them, and we will go through them in the next video.